Some words become so familiar that we stop asking what they actually mean. And force is one of those words. We say strong punch, strong engine, strong wind, strong attraction. And after hearing the word in so many places, it begins to sound obvious, almost like a hidden power stored inside objects. But the moment you ask one simple question, what does force actually do? The familiar picture begins to break. A book lies on a table, you push it with your hand, and it starts moving. Then you stop pushing. And after a short moment, the book stops. Everyday experience seems clear. When there is force, there is motion. And when the force disappears, motion dies. But this is where our intuition betrays us. In classical mechanics, force is a vector quantity that describes an interaction capable of changing the momentum of a body. More precisely, force is the rate at which momentum changes. Written as force equals the change of momentum over the change of time. If the mass stays constant, this becomes the familiar formula: force equals mass times acceleration. This definition sounds technical, but the central idea is simple. Force is not the reason an object has motion. It is the reason its motion changes. A push does not explain why motion can exist. It explains why the book changes from resting to moving. And the book does not stop because motion naturally runs out. It stops because another interaction acts on it. Friction. Friction is the quiet character in this story, and we are so used to it that we almost forget it exists. It constantly slows objects down, turns mechanical motion into heat, and creates the illusion that motion needs support. If we remove friction, remove air resistance, and remove everything that disturbs the body, the picture changes completely. An object that is already moving does not need to keep receiving force in order to continue. It simply continues moving. And that is inertia. Inertia is not hidden energy or stubbornness. It is the tendency of a body to preserve its state of motion, which means that rest and uniform straight line motion are both states that do not change. For physics, an object resting calmly on a surface and an object flying uniformly through empty space have something essential in common. Their motion is not changing. And if the motion is not changing, the net force can be zero. We usually think motion needs a cause. But in Newtonian mechanics, change of motion needs a cause. If velocity is constant and direction does not change, we do not need a force to explain the motion. We need a force when the body speeds up, slows down, turns, falls, stretches, or deforms. Velocity is also more subtle than everyday language suggests, because it is not just a number on a speedometer. Velocity is a vector. It has magnitude and direction. So even if the magnitude stays the same, the velocity can still change if the direction changes. Imagine a car moving in a circle. The speedometer may show the same value all the time, and the car is not getting faster in the ordinary sense, but it is constantly turning, so its velocity vector changes every moment. If velocity changes, there is acceleration, and the turn is just as much a result of force as speeding up or braking. It only feels less obvious, because we often use the word acceleration as if it only meant going faster. But in physics, acceleration means any change of velocity, a change in size, a change in direction, or both. That is why the force acting on a car moving around a curve is directed toward the center of the curve, not simply forward along the road, because this force does not necessarily make the car faster. It changes where the car is going. The same idea becomes even more striking with an orbit. Because a satellite does not move around Earth. Because some mysterious force pushes it forward. It moves because gravity constantly bends its trajectory. The satellite is falling toward Earth. But because it also has sideways motion, it keeps missing the ground. So an orbit is not motion without force. It is motion whose direction is constantly being changed by gravity. Force is not a thing inside an object. It is not a substance. And it is not a reserve that a flying ball carries through the air. A ball can have velocity, momentum, and kinetic energy. But it does not have force in the same way it has mass. Force appears when there is an interaction. Your hand acts on a ball during a throw. Earth acts on a stone through gravity. A table acts on a book through the normal force. And air acts on a falling object through resistance. In every case, force describes how one body, field, or system changes the motion of another. That is why the question, what force does this body have, is often misleading. Better questions are, what is acting on this body? What is it interacting with? And in what direction is this interaction changing its motion? The arrows in school diagrams can also create confusion. Because a force arrow may look like a small object glued to another object. But it is only a language. It represents the magnitude and direction of an interaction. If the arrow points to the right, that does not mean the body must be moving to the right. It means the body's motion is being changed in that direction. This is why a body can move right, while the force acts left. A ball rolling across the floor may move to the right, while friction acts to the left. Because motion and force do not have to point in the same direction. What must align in the simplest constant mass case is force and acceleration. Because acceleration tells us not where the object is moving, but how its velocity is changing. If force acts against the motion, the object slows down. If force acts sideways, the path curves. And if force acts along the motion, the object speeds up. One idea unites all of these cases. The net force determines the change of motion. This is why force equals mass times acceleration is much more than a formula to memorize. It says, do not only look at where the object is already going, look at how its motion is changing right now. Mass then enters the story as a measure of inertia. Because the larger the mass, the harder it is to change the object's motion. The same push may accelerate a light box, but barely affect a heavy cabinet. Because the same force produces a smaller acceleration when mass is larger. And the opposite is also true. If we observe a large acceleration, then either the force is large, the mass is small, or both. A tiny dust particle can be dramatically redirected by a weak air current, while a massive stone barely notices the same disturbance. Everyday life constantly gives us the wrong intuition, because we do not live in empty space. We live among rough surfaces, air resistance, rolling losses, muscle effort, and imperfect machines. Almost everything around us slows down, unless we keep pushing it. So it feels natural to think that motion is unstable and must be constantly maintained. But that is not a fundamental property of motion. It is a property of our environment. Think about riding a bicycle on a flat road. While you pedal, the bicycle keeps moving. And when you stop, it slowly loses speed. It is tempting to say, pedaling creates motion, and without pedaling, motion disappears. But your legs are not supporting motion itself. They compensate for losses, wheel friction, tire deformation, air resistance, and tiny imperfections of the road. If those losses disappeared, the bicycle would not need continuous effort, because the effort is needed only when the environment constantly steals energy from motion. If you like what I'm making, and you want the animations, visuals, explanations, and voiceover to become better and more detailed, you can help by hitting those two funny little buttons, like and subscribe. It helps the channel grow and helps me buy better assets, because apparently cool visuals cost real money.